In the previous video, I discussed the selection of the drives. Now from this video onwards, I shall discuss design of different types of gearings. I start with Spur gearing, which is the simplest of the all gearings. It is to note that most of the fundamentals which I shall discuss here are also applicable to other gearing types, of course with some modifications. As discussed in the video on selection of drives, the gearing provides a constant speed ratio. In the gear drive, motion is transmitted from one shaft to another by means of direct contact of two toothed wheels. You can refer the figure on the first page. In an operating pair of gears, the teeth of one of the gears enter into the spaces between the teeth on the other gear. The smaller of the two gears is termed as pinion and the larger one as gear, although both of them are gears in a strict sense. Spur gearing is most widely used gearing for low to medium power and speed applications because of its relatively low cost and simplicity. The shafts carrying these gears must be parallel to each other and they must lie in the same plane. The speed reduction up to 6 is generally considered as a good design practice for this gearing, but for low speed applications a higher speed reduction may also be allowed. Figure 1 shows a pair of teeth in mesh. Since the teeth surfaces in contact are curved, the driver tooth exerts force Fn on the driven gear tooth in a direction normal to the surfaces in contact. The load Fn has been resolved into its components: tangential tooth load Ft and radial load Fr. It is to note that involute profile is most widely used for the teeth. I shall discuss the involute profile and its characteristics in the next video. When we design any machine component, it is essential to know the various ways in which the component may fail. Here I discuss the various modes of gear tooth failure. The first mode of failure may be the bending of tooth under static loading. The tangential component Ft of the tooth load causes bending of the tooth, which acts like a cantilever. Hence, the tooth may fail under bending stress. The tooth may deform to such an extent that improper tooth action may occur. It is to note here that the gears are produced with good accuracy. Hence, if deformation of the tooth under load occurs, the gearing action is impaired. Then, if teeth are made of a ductile material, permanent deformation of the tooth may take place if it has not adequate strength to take this bending load. The second mode of failure to be considered is fatigue of the tooth. Though the tooth load is variable in nature, it may be treated as static if the gears do not run at appreciable speeds. For the gears rotating at appreciable speeds, The tooth may experience fatigue failure, which causes the uprooting of the tooth. It is the worst type of gear tooth failure because the drive immediately stops and the gear is rendered useless. The fatigue crack starts at the root on the tension side of the tooth. As shown in figure 2, the crack slowly progresses towards the core with the passage of time. Finally, the tooth becomes so weak because of the reduction in cross-section of the tooth that fracture takes place and the tooth is uprooted. The third possible mode of failure of the gear tooth is the wear. The wear of the tooth surface may appear as scratches on its surface, pitting of the tooth surface. The pitting is basically surface fatigue of the tooth. Reduction of the thickness of the tooth due to normal wear. In normal wear, the surface of the tooth remains smooth. Note that the gear will not run forever. Out of the three modes of failure discussed here, the normal wear must be the only cause of the retirement of a gear. In this slide, I have tried to explain what happens at the surfaces in contact which causes the wear of the teeth surfaces. During the engagement of the teeth, the driver tooth moves, rubbing the surface of driven gear tooth from the tip towards the root. See the arrow indicating the relative motion in the figure. During the disengagement, this action is in the reverse direction. In the nutshell, it is to note that the grains of the surface are pushed first in one direction and then in the reverse direction, and this causes the fatigue of the surface. The intensity of the contact pressure and the change in the direction of the rubbing action dictate the surface fatigue. Proper lubrication helps in the control of the rate of normal wear and the scratching of the tooth surface. The abrasive particles must not get access between the rubbing tooth surfaces. That is, the lubricant must be free of such particles. We discussed the various modes of failure of the gear tooth. The first mode of failure discussed was due to the bending stress. Here we will see what is the bending stress induced in the tooth, and finally this will lead us to a design equation known as Levis beam equation. The worst loading condition of the tooth occurs when the normal tooth load Fn acts at the tip of the tooth as shown in the figure. In the figure it can be seen that line of action of the normal tooth load Fn has been extended to cut the central line of the tooth at point C. The components Ft and Fr can be assumed to be acting at point C. The radial component Fr of the load induces compressive stress sigma c in the tooth body. while the tangential component Ft acting at point C, which is at distance h from the root of the tooth. So the maximum bending moment due to Ft will be Ft into this distance h, and the maximum bending stress will be at section DE of the tooth. In figure, the stress distribution is also shown. The first curve refers to the bending stress. The left hand side is tension side and right hand side is compressive side. The second curve of stress distribution is that of the compressive stress, which has been assumed to be uniform throughout. The third curve of the stress distribution shows the combined effect of bending and compressive stress. In the fourth curve, the bending stress and compressive stress have been multiplied by factor Kf, which is known as stress concentration factor, and I shall discuss the stress concentration factor later on. We have seen that the tangential tooth load induces bending stress, which is maximum at section DE. Hence, the bending stress will also be maximum at this section, and it is given by equation 1, where m is the bending moment, which we have already discussed as Ft into h, and z is the section modulus at the root of the tooth. For beam width B and tooth thickness T, the section modulus is 1 by 6 Bt square. Remember that the section of the tooth at the root is rectangular. It is to note that the compressive stress has been found to be much smaller in magnitude compared to the bending stress. Hence, for the further discussion and analysis, I shall neglect this. The equation 1 can be rewritten as Ft is equal to sigma b into beam width b multiplied by t square divided by 6h. The factor t square divided by 6h is a geometric property of the tooth, that is, a function of the size and profile of the tooth. The factor is expressed as a function of the pitch of the teeth by the relation t square divided by 6h is equal to pc into y, that is equal to pi my. In equation 3, m is termed as module, and as per the definition, the module of a gear is its circular pitch Pc divided by pi. From the figure 5, it can be seen that the circumference of the pitch circle is pi d, and if gear is having number of teeth z, then the circular pitch Pc is equal to pi d divided by z. Substituting the value of Pc in equation 4 and simplifying, we get that module is equal to d by z. The factor y in equation 3 is known as Levis form factor, and it is a function of the number of teeth on the gear and the pressure angle. The pressure angle will be defined in the next video. The equations for the determination of the value of factor y are also given in the next video. Using equation 3 in equation 2, we get Ft is equal to sigma b, b pi by m. And this is the basic design equation considering the bending stress only. This equation is known as Lewis beam equation, which considers the bending load on the gear tooth to be of static nature. As discussed earlier, the load on the tooth is dynamic in nature. It varies as the engagement of the teeth proceeds from its tip to the root and also when disengagement takes place. Further, there is no load on the tooth when it is not in mesh. Thus, it goes through the cycles of the loading and unloading. The time of load cycle is the time of one revolution of the gear. To take account of this dynamic effect of the load, the Lewis beam equation is modified. This will be presented in the next video. For greater details, you can refer the reference given here. I hope you have liked the video. Please feel free to send your questions at my email address given on the first page. Please wait for the next video. Thanks.